Hello everyone, I am Dhanush, studying in the 8th semester of Mechatronics, Sri Venkateshwara College of Engineering. I am here today to present to you a technical seminar on the topic of quantum computing, guided by Professor Suresh DB. The contents of this technical seminar include abstract, evolution of quantum mechanics, interpretations of quantum mechanics, the basics of classical computing, the transcendence of quantum computing, the qubit and its properties, quantum gates, IBM's quantum computer, applications of quantum computer, limitations of quantum computer, and conclusion. Now coming to the abstract of the seminar, quantum computing is a field of study that aims to develop computers that use quantum mechanical phenomena to perform computations at a much faster rate than classical computers. Quantum computing is based on the principles of quantum mechanics, which allow quantum bits or qubits to exist in a superposition of states, enabling them to perform multiple calculations simultaneously. Quantum computing has the potential to solve complex computational problems that are currently beyond the capabilities of classical computers, such as simulating large-scale chemical reactions or breaking encryption algorithms. Despite the progress made in quantum computing research, the technology is still in its early stages and faces numerous challenges, including the need for error correction and the development of scalable quantum hardware. Now coming to the evolution of quantum mechanics. Firstly, talking about the historical development of quantum mechanics. In the late 19th and early 20th centuries, physicists were struggling to explain several phenomena that could not be explained by classical physics. In the scientific context, the development of quantum mechanics was largely driven by the failure of classical physics to explain certain phenomena at the atomic and subatomic levels. As physicists began to study the behavior of particles at the atomic level, they found that classical physics was inadequate for explaining their observations. The spectrum of radiation emitted by heated objects and the photoelectric effect were one such examples of failure. The Heisenberg's uncertainty principle was also one of the major failures of classical physics. There were several key contributions made to the field of quantum mechanics by many of the prominent scientists during the early 20th century. Firstly, Max Planck came up with the quantum of action and the wave-particle duality theory. Albert Einstein stated the quantum entanglement theory. Niels Bohr came up with the Bohr's atomic model and the Copenhagen interpretation. Werner Heisenberg stated the Heisenberg's uncertainty principle. Arun Schrödinger came up with the Schrödinger equation and the cat-thought experiment. Paul Dirac proposed the wave mechanics. There were many interpretations made in the field of quantum mechanics, and let's discuss some of those in the following sections. The first one is the Copenhagen interpretation. We all know that any quantum system can behave as both a particle and a wave, and every quantum system is supported by a wave function. This Copenhagen interpretation suggests that a wave function collapses into one of the probable states of the quantum system upon measurement. The second one is the many worlds interpretation. It states that every possible outcome of a quantum measurement occurs in different universes or worlds. This basically suggests that there are many number of universes present around us, and the quantum systems in each of these universes are connected to each other, and the outcome of each of these quantum systems appear at least once in each of these worlds. The third one is the pilot wave theory. This theory proposes that every particle in the quantum realm is guided by a hidden wave which is determined by the Schrödinger equation. The fourth interpretation is the transactional interpretation. In the transactional interpretation, quantum mechanics is viewed as a series of transactions that take place between the emitter of a quantum particle and the absorber of that particle. Coming to the basics of classical computing. Now, what are classical computers made of? They are made of integrated circuit chips, which are made up of basic modules, and these modules contain a number of logic gates, and each of these logic gates is built using a couple of transistors. Now, what is a transistor and how does it work? A transistor is basically a channel for the flow of electrons. When the electrons are allowed to flow through the channel, it is considered to be a high state, and when the electrons are not allowed to flow through the channel, it is considered to be a low state. Now let's talk about the transcendence of quantum computing. Here are the basics of quantum computing. Quantum computing is a paradigm that uses principles of quantum mechanics to perform computations, as mentioned before. In classical computing, information is processed using classical bits, which can take on values of either 0 or 1. Quantum computing, on the other hand, uses qubits or quantum bits, which can exist in a superposition of states. Qubits can also be in an entangled state. One of the key challenges in quantum computing is building and maintaining stable qubits. Despite these challenges, quantum computing holds great promise for a wide range of applications, from cryptography to drug discovery to artificial intelligence. Now, the qubits are the basic building blocks of quantum computer, and these qubits have certain properties which make up the quantum computer. And let's discuss those properties. The first property is the superposition and measurement. Now, as we already know, superposition is a state where a quantum bit or a qubit can exist in multiple states at the same time. And now a regular bit has only two possible states, which is the 0 or the 1, or the low charge or the high charge. And these bits can only stay at one single level at any given time. But the qubits are unlike this, wherein the qubits can exist both in the 0 state and the 1 state at the same time. Now these qubits can be made up of any subatomic particles, such as an electron, which has an upspin or a downspin, or a linear or a rotational magnetic field. Or it can even be made up of a photon, which has a vertical or a horizontal polarization. And these vertical or horizontal polarizations can happen at the same time. And whenever this photon is allowed to pass through a polarization filter, it has to decide whether it moves through a horizontal polarization or a vertical polarization, and this causes a measurement collapse. The superposition collapses into one particular state after it is measured. This is called superposition of state, being both in the zeroth state and the one state at the same time. And as soon as you measure the state of the qubit, it collapses into one of those probable states and gives you the output. We all know that a qubit can exist in a superposition of state, and how can this be an advantage to us? Consider these 4 bits of classical bits, in a classical computer. Now these 4 bits can be set to any of the 16 possible combinations as follows. And at any given time, you can choose only one of those 16 combinations to perform calculations. But unlike this, in a quantum computer, these 4 qubits can store all the 16 possible combinations at the same time and all the 16 combinations can be accessed at the same time. Now, as the number of qubits increases, let's say for example 20 qubits can already store more than a million common configurations at the same time. Next property is the quantum entanglement of a qubit. You already know that quantum entanglement is a state where two quantum systems are connected to each other and their properties are also connected to each other. When a quantum bit is entangled with each other, their properties and also the probability of their output are also dependent on each other. When one quantum bit measures to 0, the other one also measures to 0. And when one quantum bit measures to 1, the other one also measures to 1. We can see here that quantum entanglement is of two types, positive entanglement and negative entanglement. In a positive entanglement, when one of the qubits measures to a particular value, the entangled qubit also measures to the same value. In negative entanglement, when one of the qubit measures to one value, the other quantum entangled bit measures to a different value or the opposite value of that previous value. We already know that quantum systems behave as both particles as well as waves. These waves of qubits interact with one another to form what is called as an interference. Now, these interference can be of two types. One is constructive interference and destructive interference. Based on the type of interference happening, the probability of output can also vary. The next property is the coherence and decoherence of qubits. Coherence is another important property of qubits in quantum computing. In simple terms, coherence refers to the ability of a qubit to maintain its quantum state over a period of time. This is crucial because any disturbance or interference with the qubit can result in loss of information or even a complete collapse of the quantum state, making it impossible to perform reliable computations. Decoherence is one of the most significant challenges in building and operating quantum computers. It refers to the loss of coherence or the breakdown of the quantum state of a qubit due to the interactions with the environment. Now let's talk about the quantum gates. Qubit manipulation using quantum gates. In classical computers, there are logical gates such as OR, AND, XOR, and other universal gates which accepts bits such as zeros and ones and perform computations based on these inputs. In quantum gates accept a superposition of a qubit, spins the possibility of the output, and provide the superposition again as an output. Now, these combination of quantum gates are used to accept superposition of inputs, spin off the probability of the outcome of that particular input, and provide a superposition of outputs to as opposed to the inputs given. Now, these outputs are also in the superposition of state, and we can access any one of those following states by measuring those particular superposition of qubits. Now, since we know that quantum computer is capable of superposition, it can access all of these computations at the same time. And by exploiting this property of superposition, we can also access all these computations at the same time unlike a classical computer wherein each of the computation should be performed one after the other. This is IBM's quantum computer, an example of a real-life quantum computer. Coming to the applications of quantum computing. When it comes to quantum computing, the applications are limitless, and here are some of the applications: cryptography, optimization algorithms, drug discovery, machine learning, traffic optimization, climate modeling, financial modeling, material science, protein folding, and artificial intelligence. Talking about the limitations of quantum computing, there are also certain limitations still when it comes to quantum computing, and those are hardware constraints, scalability, error correction, limited algorithmic development, and high cost. Concluding this topic, in conclusion, quantum computing represents a promising new frontier in the field of quantum computing. Its unique properties and capabilities have the potential to revolutionize a wide range of fields, from cryptography and drug discovery to financial modeling and optimization. While significant progress has been made in building larger and more reliable quantum computers, there are still significant challenges that must be overcome before quantum computing becomes a widespread reality. Despite these challenges, the growing interest and investment from both the academia and industry suggests that the future of quantum computing is bright. As more researchers and developers work on the potential of this new technology, we can expect to see even more exciting breakthroughs and advancements in the coming years. Overall, quantum computing represents a fascinating and rapidly evolving field that has the potential to fundamentally transform the way we approach some of the most complex computation challenges facing society today. As such, it is an era that is well worth exploring further, both for its potential impact on industry and society, as well as for its inherent intellectual interest and scientific curiosity. These are the references taken while preparing this presentation. That's it. Thank you.